So in the last few lectures, we looked at how to work out the stiffness matrix for some simple elements like the truss elements, for example. Now, the way we work it out is quite unique to elements with those type of shapes. But generally, if we want to work out the stiffness matrix for a element of arbitrary shape, and most typically, for example, we use square and triangle elements where the element is continuously distributed with mass inside each element. Those ways of working out the stiffness matrix doesn't really help to work out this K matrix for this type of elements. So a way to get around this, or a way to make this more tractable or pragmatic to work out the stiffness matrix, is to apply the principle of virtual work. Now, the concept of the virtual work is quite abstract and sometimes a little bit hard to understand. And what we're going to go through here is just some of the basic idea and simplest way to understand why these things comes about. Okay. There are many tutorial videos online that I watch to try to understand the concept of virtual work, but I found out the way they explain as following will be the easiest for us to understand how this thing is linked up with the finite element analysis. So first thing, we need to go back to the concept of work that we learned from first year mechanics. Now, by definition, the work done by external force is the product of the force dot the displacement that the object has undergo, and you integrate it or sum it across the path that the object has been moving. So, for example, if I have a floor here where I have a system, a block with mass m, and I apply a force F, which forms an angle theta with the x-axis. And under this force, what happens is that this block will start moving, and say you move to this place by a distance of s. Right? So the work done by these external forces is F dot S, which in this case is the magnitude of F times the magnitude of S dot cos theta. Alright, so this is what we understand in terms of the first year physics. But in a system where, or in a mechanical support system, the mechanical support system, for example, I have a system with 3 nodes A, B, and C. Now A and C are fixed in position, and I have a bar element that goes to B, and another bar or truss element goes to C. Now in this case, there will be some sort of loading on B and some sort of loading on A and C as well. But the system is in equilibrium, so there's actually no work done to the system because the system is not moving, right? So you can use the balance of forces to say all these forces are balanced, which we know, but that's not helping us to work out what's the actual deformation that's going to occur in this system, right? So the forces are balanced, and there's no displacement. So by that we say there's actually not moving. So if it's not moving, that means the work is actually zero, right? But we know that's not helping us to solve the problem because the force actually exists, right? The force exists. And what it does is actually induce deformation in the structure, right? So the energy applied, or the energy given by the external forces applied to this element, is inducing some sort of deformation in the system. So there are some elastic or strain energy stored in the system, right? We know that the strain energy will be proportional to what? The strain that applied on the structures times its deformation, right? So this something somehow need to link to the force done by the work done by the external forces. But we can't really use this approach to work out the forces or the energy given by the external forces, but because the structure is not moving, right? So what we do is to think about what happens if these forces induce a very, very small, maybe I use another color, use a very small displacement, or what we say a virtual displacement, delta B. Or here we just imagine some small displacement has indeed been induced by on this forces or the node that's moving. So we can say now with a virtual displacement on node B, which is delta B, what we can say is we can now say the external work or work done by external forces. Now you notice that A and B, I didn't put any virtual displacement there because they are fixed. So in this case it will be FB dot delta B, right? So that will be our external forces, but it's virtual, right? So now what do we get? Well, the thing we'll get now is basically saying that if the system is in equilibrium and we have some external forces, the force induced or the virtual work induced by the external forces must be fully translated to the strain energy of this truss element or the structures we have. So that means we have the external work done by the external forces equal to the internal energy being stored in this system, whereby this W external is our FB times delta B, and this guy here is basically our strain energy in the system. So we need to sum up across all the elements we have. So this is basically a very sort of hand-wavy idea of what we try to achieve with the principle of virtual work. And then in the next video, we're gonna look at how we actually gonna link up this idea to what we need in finite element analysis. That's basically how this can help us to calculate the stiffness matrix for an element in FEM.